Good morning, dear students. Our next session that is regarding the kinetics of hydrogen-chlorine reaction. Okay. Sometimes you have heard of this hydrogen-chlorine reaction, and also this reaction, the photochemical combination of this reaction, it was studied by the scientist named Nernst. Okay. So here in the case of hydrogen-chlorine reaction, the equation we can write it like this: hydrogen gaseous state plus chlorine, it is also in the gaseous state, to give 2HCl. Okay, again in the gaseous state. And also this scientist Nernst, he has devised a mechanism for this particular reaction. Also mechanism for this reaction, and also the mechanism, it is a free radical mechanism. Sometimes you have heard of this mechanism, free radical mechanism, and also it includes 3 steps. The first step, that is the chain initiation step. Chain initiation step. And also in this step, this chlorine molecule, it will be absorbing a photon, that means a light radiation. A particular quantum of energy it will be absorbing. This chlorine molecule, it will be absorbing some energy from the photon, that is h nu. Okay, so that this chlorine molecule, see chlorine, we can write it as Cl, single bond Cl, isn't it? When this chlorine molecule, when it undergoes homolytic fission, fission means breaking of bonds, homolytic fission means, see, one bond is formed by the combination of 2 electrons, isn't it? Here it is by the sharing of 2 electrons. So by homolytic fission means the bond breaking will be takes place in a symmetric manner. That means here the bond is broken and each of the electron will be moving towards each of the chlorine atom. Okay, so each of the chlorine atom will be getting 1 electron each. So that we will be having how many free radicals? 2 chlorine free radicals. Okay, so each of the chlorine atom will be getting 1 electron each. Okay, so when this chlorine atom, when it is absorbing a photon, or when it is absorbing a photon, this chlorine molecule, it will be forming, we will be having 2 Cl dots or 2 Cl free radical. So this free radical, it is denoted by this dot. Okay, so this chlorine free radical, this will be act as the chain initiator. So in this reaction, this chlorine molecule, chlorine free radical will be initiating that particular reaction. Okay, so we can put it as equation number 1. And in the second step, we have got propagation. Okay, second step, that is the chain propagation, that is the free radical formation, it will be going on continuously in the second step. So in the first step, we had got 2 chlorine free radicals. Okay, so one of this chlorine free radical, it will be combining with a hydrogen molecule. Okay, so here one of the reactants, it is hydrogen molecule. So this chlorine free radical, it will be combining with a hydrogen molecule. So on combination, what happens? Again, this hydrogen molecule means it will be like this, H, single bond H, 2 electrons will be shared. So while this bond, when it is broken, what happens? 2 H dots will be obtaining. We will be having 2 H free radical. And again, from this, 1 hydrogen free radical, it will be combining with this chlorine free radical. Okay, so one of this hydrogen free radical, it will be combining with a chlorine free radical. What will be the product? The product will be HCl, isn't it? So the product, we will be obtaining HCl. So the remaining one will be 1 H free radical. Okay, hope you are clear. This hydrogen molecule on homolytic fission, we will be having 2 H free radical. That means 2 H dot. Then again in the next step, one of this H dot or H free radical, it will be combining with this chlorine free radical. So that we will be having HCl plus the remaining will be 1 H dot. Okay, so here we will be having HCl plus H dot. Okay, so this is the second step. Okay, so this is the second step in the chain propagation. Then in the third step, again 1 H dot will be there, isn't it? So in the third step, this H dot will be combining with the next chlorine molecule. Okay, chlorine molecule is another, is this reactant molecule, isn't it? So what happens here? Chlorine molecule means, again we can write it as Cl2 or Cl, single bond Cl, on homolytic fission we will be having 2 Cl dots, and again one of this Cl dot, it will be combining with 1 H dot, isn't it? Again we will be having 1 HCl molecule, and the remaining one will be 1 Cl dot, isn't it? Here 1 Cl dot will be remaining. So that is the third step in the in this reaction, okay, and also second step in the propagation stage. So here we can see 2 free radicals we will be obtaining, that is H dot or H free radical and chlorine free radical, isn't it? 2 free radicals are there, that is H dot as well as Cl dot. So we can say that these two, they are called as the chain carriers. This hydrogen free radical and the chlorine free radical, they are called as the chain carriers. So these two radicals will be propagating the chain, or it will be making the reaction go on in a continuous manner. Okay. So here in the, this chlorine as well as hydrogen will be acting as the chain carrier, and again see, for this reaction, due to the presence of these chain carriers, what happens is that the quantum yield will be very high. We had seen in our last session, isn't it, the quantum yield or the quantum efficiency. So here we can say that the quantum yield is very high. That means due to the with the expense of a single photon, see how many products are formed. See, 2 molecules of HCl are formed, isn't it? And again in the last step, the third step, that is the termination step. That means the reaction will be ending at this stage. Okay. So the third step is the termination step. So at this stage, what happens is that this chlorine radical, it will be combining with, see here one more chlorine radical is there in the first step, isn't it? So it will be combining with another chlorine radical to form Cl2. Okay. So 2 chlorine atoms or 2 chlorine free radicals will be combining together to form a chlorine molecule. And also here, so at this stage, what happens, the reaction will be coming to an end. Okay. So 3 steps are there. The first one, initiation, second one, propagation, and the third one is the termination. So here, see, number of HCl molecules formed. See, at the expense of a single photon, how many HCl molecules are formed? 2 HCl molecules are formed, isn't it? So this is an example. So likewise, we can say that the quantum yield or the quantum efficiency. So the quantum efficiency, it is denoted by phi, isn't it? So the quantum efficiency for this particular reaction, for this hydrogen chlorine reaction, normally it will be between 10 raised to 4 to 10 raised to 6. Okay, so the quantum yield, we can say that it is very high for this particular reaction due to the presence of the chain carriers. Okay, and also we can say that the rate of the reaction, it will be directly proportional to the intensity of the absorbed radiation. If the absorbed radiation is of high intense, then we can say that the rate of the reaction will be depending on the intensity of that particular radiation. Okay, so this kinetics of hydrogen chlorine reaction, it is very simple, and also it will be asked in your section C part, okay, for 4-mark question. And also you have to remember only these 3 points: chain initiation, then chain propagation, as well as chain termination. Okay. So next topic, that is the photosensitization. Photosensitization. See here, photosensitization means, for example, see in this reaction, see mercury molecule, it will be absorbing a photon. That means a quantum of radiation this mercury will be absorbing, and this mercury, it will be excited. Excited means it is denoted by an asterisk mark. Okay, so that this mercury, it becomes an excited molecule, excited atom. Mercury becomes an excited atom. And again, this mercury vapor, when it is shown over hydrogen molecule, or when this excited mercury atom, when it is treated, or when it is exposed to this hydrogen molecule, what happens is that this mercury vapors, or the excited mercury vapors, it will be passing the energy, or it will be transferring the energy to this hydrogen molecule. Okay, so what happens is that this energy will be transferred to hydrogen molecule, so that this hydrogen molecule will becomes excited, and then again mercury will be moving towards the to the ground state, or it will be in the de-excited state, okay, or it will be deactivated. And again in the next step, this excited hydrogen molecule, it will be converting or it will be dissociating to form 2H free radicals. So here the hydrogen molecule, it will be dissociated to hydrogen atoms. So here dissociation of the hydrogen molecule takes place, isn't it? Dissociation of hydrogen molecule takes place with the help of mercury. See here, this mercury is absorbing the radiation, the quantum of radiation, isn't it? This mercury will be in the excited, by absorbing the radiation, it will be moving to the excited state, isn't it? That means the mercury is not directly involving in that or directly taking part in that particular reaction for the dissociation of hydrogen atoms, hydrogen molecule, isn't it? Here the reaction is dissociation of hydrogen molecule. So here this mercury is not directly involved, but it is absorbing the energy from that particular radiation and it is transferring to the hydrogen molecule. Thus hydrogen will be going to the excited state and then again it is dissociated to hydrogen atoms, isn't it? So here mercury acts as a photosensitizer. Mercury acts as a photosensitizer. What do you mean by photosensitizer? Photo means light, isn't it? So it is mercury, it is a light sensitized substance, isn't it? So when light falls on it, it will be excited. So it is a photosensitizer. That is, when it is exposed to light, it will be moving to a higher energy state or it becomes an excited atom, isn't it? So mercury acts as a photosensitizer, and this type of reactions we can call it as a photosensitized reaction. It is called as a photosensitized reaction, or simply the phenomenon we can call it as a photosensitization. Photosensitization. Okay. So this is the example behind this photosensitization. So we can say that photosensitization means, or a photosensitizer means, a species which can absorb and transfer energy. A species which can absorb and transfer energy to the reactant molecule. So here the reactant molecule is hydrogen, isn't it? A species which can absorb and transfer energy to the reactant molecule. and also see here, does mercury undergoes any change? No, isn't it? It only gets excited and then again it will be back to its ground state, isn't it? No change in the case of mercury is there, isn't it? So this is just like a catalyst. That means this will be absorbing and transferring the energy to the reactant molecule. At the same time, it does not undergo any chemical change. It does not undergo any chemical change. Okay, so this is called this type of reactions we can call it as a photosensitized reaction, or the phenomenon is called as photosensitization. So photosensitizers are substances or species which can absorb and transfer energy to the reactant molecules. So here mercury acts as the photosensitizer, and also it does not undergo any chemical change. So you have to write the example also while you are asked to write the photosensitization for a 4-mark question. Okay. And the next phenomenon, that is the photoinhibition. Photoinhibition. Photoinhibition means, see, inhibition means it is just, the word meaning itself, it shows that it is just the prevention, isn't it? Or it will be preventing from a particular reaction. So photoinhibitor means if such substances, if photoinhibitors or such chemical substances are even present in a trace, in the case of a photochemical reaction, if such substances or some chemical species are there which retards the rate of a reaction, if the rate of the reaction, if it is decreased, the rate of the reaction is decreased. Rate of the reaction means here it is the rate of the photochemical reaction. So if the rate of the photochemical reaction is decreased by any other foreign substance or any other chemical species, we can call it as a photoinhibitor. So photoinhibitor means it will be reducing the rate of a photochemical reaction. Such substances are called as photoinhibitors, and the phenomenon it is called as photochemical inhibition. Okay, photochemical, it is photochemical, okay, sorry, photochemical inhibition, photochemical inhibitor or photochemical inhibition. Okay, so such substances, see, in the case of already we have seen a hydrogen chlorine reaction, isn't it? So there the chain carriers are hydrogen free radical as well as chlorine free radical. So in such reactions, if a photochemical inhibitor is there, that means for example in such reactions, nitric oxide, NO, nitric oxide, then propylene. Propylene means it is a double bonded compound, isn't it? Propylene with 3 carbon atoms, CH3, C double bond, C single bond, CH3, here CH, CH2. So this is propylene. Okay, it is a double bonded compound. Okay, if such substances are present in hydrogen chlorine reaction, what happens is that the rate of the reaction will be decreased, or the reaction will be prevented from going on. So what happens is that these photochemical inhibitors, we can call it as nitric oxide as well as propylene, as photochemical inhibitors. So due to the presence of these substances, what happens is that this will be removing, these photochemical inhibitors will be removing the free radicals from that particular reaction. So that what happens, if the free radicals are removed from that particular reaction, what happens, the chain or the reaction chain will not be propagating, or the reaction will not be going on continuously. So the reaction will be prevented from taking place, or the rate of the reaction will be decreased. So such substances we can call it as a photochemical inhibitor. So in general, we can say that photochemical inhibitors are the substances which inhibits the rate of a reaction, or which decreases the rate of a photochemical reaction. Example, in hydrogen chlorine reaction, nitric oxide, then propylene, etc. will be acting as a photochemical inhibitor. So here what happens is that due to the presence of these photochemical inhibitor, it will be the quantum yield of that particular reaction will be low if photochemical inhibitor is there. Okay, if photochemical inhibitor is present, photochemical inhibitor, okay, if photochemical inhibitor is there, the quantum yield or the quantum efficiency will be low. So then the next topic, that is chemiluminescence. Okay, chemiluminescence. See, chemiluminescence, it is just the opposite of photochemical reaction. It is just the reverse of photochemical reaction. Photochemical reaction means the chemical reaction taking place in the presence of light, isn't it? Here chemiluminescence means as a result of a chemical reaction, light will be produced. Okay, so first chemical reaction will going on, and as a result of chemical reaction, what happens, light will be produced. That is called as chemiluminescence. You know a very common example for bioluminescence, isn't it? Bioluminescence. A very common example for bioluminescence, you know. And also see here, chemiluminescence means it is just the reverse of photochemical reaction. That means as a result of the chemical reaction, this light will be produced, or chemical reaction brings about emission of radiation. And also one example is given, that is when a stream of atomic hydrogen falls on the surface of liquid mercury. Okay, that is, this is mercury, and when a stream of atomic hydrogen means hydrogen atom. So what happens is that this mercuric hydride will be formed, HgH. So here this HgH, it will be combining with again it will be combining with hydrogen atoms, atomic hydrogen, so that this HgH will be gets activated. It will get activated. That means it will be having some energy. And this activated HgH molecule, this hydride, mercury hydride, it will be showing a blue luminescence. Okay, this activated mercuric hydride, it will be showing a blue luminescence plus H2. Okay, so this is the reaction for, this is an example for a chemiluminescence. That is, when a stream of hydrogen vapors, when it is passed over mercury, what happens? It will mercuric hydride will be formed. Again, when it is combining with another hydrogen atom, this activated mercuric hydride will be formed, and this activated mercuric hydride will show a blue luminescence. That means a blue shining will be there. So this is an example for a chemiluminescence. Then, so in this chapter, one more portion is there, the remaining portion, that is the enzyme catalysis. You have to study in detail this enzyme catalysis and also one mechanism. And the equation also, that we can study in our next session. And also, see, I am posting one assignment also. So you have to do that assignment and submit it before the due date. Okay, I will be giving some 2 or 3 questions. You have to answer it and submit it through your Google Classroom. Okay, thank you.